this is Mrs. Basin, and today we're going to talk about heat and changes of state. So before we start talking about changing states, let's go back and review one more time the states of matter. So solid, if you remember, has a definite shape, definite volume. The particles are moving because we talked about how the particle motion doesn't stop until you hit absolute zero. So the particles are still moving just a little bit, and we say that the particles vibrate. They have very low energy. A liquid has no definite shape and no definite volume, and the particles are free to move. They have a little more energy. We say they have medium energy. And then a gas has no definite shape, no definite volume. Particles have a lot of random motion, and they have very high energy. So the first video we'll see is of a solid. So these are ice cubes. So you can see when it's poured into another container, they maintain their shape. They keep their volume. So they're not changing to fit the container that they're in. So for the liquid state, you can see the particles have a little more motion. They don't have a definite shape, but they do have a definite volume. So the volume stays the same, but they take the shape of the container that they're in. The last example is a gas. So for gases have no definite shape, no definite volume. You can see the particle motion is a lot higher. They don't take the shape of the container, and they take the volume of wherever they are. So when you have a substance changing from a solid to a liquid to a gas, energy is transferred. So if you were going in this direction, so if I'm going from a solid to a liquid to a gas, those types of changes are going to be endothermic. So what that means is energy has to be put in to go from a solid to a liquid, because the solid particles have less energy than the liquid. And then to go from a liquid to a gas, more energy has to be put in because the gas particles have more energy. If you go in the opposite direction, those changes are exothermic, because you're going from a higher energy to a lower energy. So as you go from a gas back down to a liquid, it decreases the energy of the particles, so that energy is released or given off. When it goes from a liquid back to a solid, more energy is released, so that would also be exothermic. We can also look at what the changes of state are called. So this is the same diagram, it just has a little different picture here. So you can see a solid is ice, liquid is water, the gas is water vapor. So when you go from a solid to a liquid, we call that melting. So solid to liquid is melting. When you go from a liquid to a gas, that's called vaporization. Another word sometimes you'll see is evaporation. Evaporation is technically vaporization at the surface of a liquid, but vaporization is probably the more correct term, but sometimes you'll see evaporation used in that place as well. And then the other change you can have going in that direction is sublimation. Sublimation is when you go straight from a solid to a gas. So the substance that's probably most familiar to us that undergoes sublimation is dry ice. It's called dry ice because it doesn't go through that liquid phase. It goes straight from a solid to a gas. When you're going in the other direction, condensation is gas back to liquid. Then freezing is liquid back to solid. And then our last change of state is one that we're probably not very familiar with. Deposition is when you go from gas straight back to solid and it doesn't go through the liquid phase first. Best example of that is frost or freezer burn. So if you see frost on your car, on the grass, or you pull a piece of meat or vegetables out of the freezer and they have that kind of freezer burn look to them, that's a good example of deposition. When we have these changes in state, there's actually energy that we can quantify that's associated with those phase changes. And that's what we're going to look at in the next section next week. So the heat of fusion is what we talk about when we're going from a solid to a liquid. So fusion, you could say another word for fusion is melting. So if you're going from a solid to a liquid, then the amount of energy required for 1 mole of a substance to be converted from a solid to a liquid is 6.01 kilojoules. So that's how much energy it takes for 1 mole of water in this case, because these are specific to the substances. So for water, it takes 6.01 kilojoules to change 1 mole of water from a solid to a liquid. The heat of vaporization is how much it would take to vaporize 1 mole of a substance. Okay, for this particular substance, and we're going to focus on water for the most part here. So for water, it takes 40.7 kilojoules per 1 mole. So again, to convert that from a liquid to a gas, 40.7 kilojoules. That number is different because if you think about the change that would be required. So up here, if we're going from a solid to a liquid, those particles are a little more spread out in a liquid than a solid, but it's not a huge difference. If you're going from a liquid to a gas, so your liquid particles are a little bit spread out, but your gas particles are way spread out. So it takes a lot more energy to spread those particles out to get them to go from a liquid to a gas than it does from a solid to a liquid. That's why that value for heat of vaporization is so much larger than the value for heat of fusion. We can use something called a heating curve to show us how these phase changes happen as a substance is heating and as heated. And next week we'll do a lab with this. So when you look at this, you have to first notice what the substance is. So every heating curve is specific to a certain substance. So this particular one is water. The reason it's specific to a certain substance is because you have to know what the melting point and the boiling points are for that particular substance. So this is water, so the melting point is 0 degrees Celsius, the boiling point is 100 degrees Celsius. So if you start out down here, this would be ice on the bottom, this would be liquid water in the middle, and then at the top, this would be gaseous water. So it starts out with an increase in temperature. So temperature increases as you're adding heat, but when you hit the phase change, it levels out. That's because even though heat is being added the whole time, anytime you hit a phase change, the temperature doesn't change because what the energy is doing is it's going in there and it's causing those molecules to spread apart. So it takes energy to overcome those forces that are holding that solid substance together. So instead of increasing the temperature at that point, that's what the energy is doing. Then your next section is the temperature is increasing again. Then you hit your next phase change. So this is where you're going from a liquid to a gas. So now you've got those particles that are already a liquid, but you need to get them to the gas phase. So notice how this line is a little bit longer than this line, and that corresponds to that larger amount of energy that we talked about that's necessary to change from something from a liquid to a gas compared to changing something just from a solid to a liquid. Then past that point, you could then heat up the water vapor, and that would then cause the temperature to increase again. Okay, so let's watch a quick little simulation here that shows how this would happen. So we're going to start out as a solid. So here's our heating curve up here. Notice during the phase change, the temperature doesn't change. Then once it's been completely converted into a liquid, you'll see on the graph the temperature will increase again. And then you'll start to see the temperature go up again. The next stopping point is going to be the boiling point where we hit 100. So this one's going to take a little bit longer to heat that from 0 to 100. You can see the particle motion here, so you can see it's a liquid. So there's some particle motion going on. Particles are still pretty close to one another. So as we get close to 100 here, as soon as we hit 100, notice the temperature change has stopped. It's flatlining out on the curve over here. And you'll see that those particles are now going from the liquid state to the gaseous state. So they're having a lot more energy, they're escaping that container. And then once that phase change is complete, now the gas is being warmed, or the gas that's close enough to be able to be warmed, you'll see your temperature increase again. So hopefully the lab we do next week will be able to see that a little bit as well. But that is called a heating curve. So as you go from a solid to a liquid to a gas, you can track that with the heating curve. Next set of notes next week that we do, we'll learn how to actually do some calculations with that heating curve. Okay, so here's another one, a little bit more detailed than that first one we looked at. Again, this is where you have your solid. Temperature stays constant at the phase change because the energy again is being used to cause the phase change, move those atoms or those molecules apart from each other so they can go from a solid to a liquid. Another increase in temperature as that liquid water is warmed up. Another flat line when you hit 100 degrees. Notice this one's a little bit longer than this one because there's more energy needed to change this from a liquid to a gas. Once all of it's been changed into a gas, temperature starts to increase again. This is where you have steam. So down here you would have solid, in the middle you would have liquid water, at the end here you would have gaseous water or steam. The other thing you can have is something called a cooling curve. So it's the same thing, it's just reversed. So in this one, you're actually starting with a gas. So you're starting with a gas, going from a gas back down to a liquid, and then to a solid. The main difference on a cooling curve is that a cooling curve has an exothermic heat value. So if you were calculating a cooling curve, you would change all those numbers to be negative. So instead of having to put in that heat of fusion, that amount of energy would be released. Same thing for the heat of vaporization. You would change that number to a negative value to show that heat was being released instead of absorbed. And we'll do a little bit of practice with those as well next week.